The next couple sessions of our book dive into simple and compound interest. My main focus for these videos is to discuss formulaic ways that you can solve interest problems, as well as why those formulas make sense, and really the different concepts behind the different type of interest. Because in the real world, uh, the different types of interest could be used in different situations, and it's kind of important to understand the differences, and also what are the implications for investing or borrowing. But the simple idea of interest is basically it's a concept that's been around for most of human history, really ever since money has ever since money has existed. But it's basically the price that you pay to borrow money that you don't have, or the amount you earn for having lent money. So say I wanted to go buy a $500,000 house in San Diego, but I don't have that much money in my bank account. How do I do it? Well, one way is to take out a loan, and basically over time pay back that loan. But most people are not generous enough to allow you to pay back only how much you borrowed, but usually you're paying back how much you borrowed plus interest. And there's some complexities that are involved with such transactions due to the nature of how percentages work. So uh, these sorts of interest calculations are always based on percent. So like an account could have, say, a 5% interest rate or something like that, which is typically an annual rate, which we often refer to as APR, which stands for annual percentage rate, which just gives you kind of how much is it growing per year. But kind of connecting back to what we talked to in the last video, we can figure out, well, how much more will be owed by applying a percentage, growth formula to it. Um, and that's basically how the different formulas work. But there are a couple different contexts of interest, which are it's important to understand the difference. And so really that there's two main types of interest: simple and compound interest. And there's a lot of different ways you can compound interest, but they're all following the same general rule. The first type, simple interest, is well, we would often refer to it in math as a linear growth function, or it's basically your account is going to be growing based on the interest rate, and it's going to grow by the exact same amount every year. So in the initial, when I initially posited an example for interest, let me pull up my calculator real quick. Um, I was saying, what if we borrowed $500,000 or something? And we wanted to know, well, what is 5% more interest? Let's say that we did not pay back any of that loan for a whole year, and we wanted to know, well, how much more is this going to be if we add 5% on top of that? And remember, kind of like with the tips from last video, we can figure out what 5% growth is by multiplying by 1.05, basically 1 plus the interest rate, which would give me a direct growth of $25,000. So basically, if I don't pay off that loan at all, I'm going to owe $525,000 after 1 year, assuming there are no penalties for not paying it back either. Which, in various situations, there could be other financial factors to take into account. But basically, the this account will grow by $25,000. So if this was undergoing simple interest, the implication would be that every single year it's going to grow by the exact same amount by the interest rate applied to the principal. A principal is just the name for what the account is starting with, like the starting value of the loan or whatever investment or whatever it is. But basically, every single year that will grow by $25,000. So the next year it would be $550,000 and so on, which is fine. But that's not how most interest works. It doesn't typically work exactly like simple interest. But basically, what it is a linear function where every year the slope of that line is the interest rate applied to the principal, and basically we can see, well, every year it's growing by that amount. So the other type of interest, which we call compound interest, is a little bit different mathematically speaking, and the formula is also a little bit different. And the difference is between linear growth and exponential growth. Compound interest undergoes what we refer to as exponential growth because over time it tends to grow, well, it doesn't tend to, it always grows a little bit faster and faster. Basically, the growth rate will increase as time progresses based on, again, the interest rate. So it's actually accounts like in what we often refer to as the nominal interest rate. Like, let's say 5% is what we refer to the interest rate. That can imply different things depending on the type of interest. Because if we're compounding interest, that 5% can be a little misleading because it actually doesn't behave the same way uh, as simple interest. And really the reason is because over time that percentage is applied to a different amount. So let me kind of explain the difference between simple and compound interest and why it works differently. But basically, let's say that every year our home loan compounds. And basically what that means is, so, okay, it started at $500,000, and let's say that we still have a 5% interest rate, so that after 1 year, our balance will be $525,000. And assuming it was compounded annually once per year, that would be the first year would be exactly the same because it would grow by its interest rate. But so what's different about this is, by the term compounding means, okay, after 1 year, my balance will be $525,000. So in the next year, the interest rate will not be applied to the principal, but the new balance. So basically, instead of growing by exactly the same amount, the bank or whoever is now treating my account as though it has this balance. And so if it's going to grow by 5%, that 5% will be applied to the new balance, not the old balance. It was just like the example of that I did in the last week about what happens if we get a raise for 5%, then another raise for 5%. It doesn't add up to a 10% raise. In the same case here, if I apply a 5% interest rate to this loan and then another 5%, that's not going to be the same amount. And this is what we refer to as compounding. So notice in the second year, after a second year of 5% growth, it's actually going to grow by a little bit more than $25,000. It looked like it grew by $26,250 because that 1.05 is applied to the new balance. And every single year, it's growing by 5%, but it's a, whoops, no, that's correct. It's growing by, basically, as you can see, every year it's multiplying by 1.05, which gives it the, which in effect adds the compounding into the equation, which was missing from simple interest. In the next video, I'll talk more about the formulas from the packet and getting into them. But in this one, I kind of wanted to set up some examples about the difference. But it's sort of like a difference between every year I'm adding an amount versus every year I'm multiplying by an amount. And that's illustrated in the different formulas in the packet. So let's go ahead and actually, I lied. We're gonna get into the formulas in this video just for a minute. And then the next videos we'll look at individual examples of using them. But basically, the simple interest formula is a linear function. So if you were to examine this, in each of these formulas, F is going to stand for the future value of the loan or account. So basically, imagine that we are investing money or we're borrowing money. P is going to stand for the principal, which is where it begins, and F is going to stand for, well, what's the end? So these formulas, they're all encoded to look very similar because they do very similar things. But in each case, the future value is going to be equal to the principal multiplied by something. And the structure of these formulas, I wanted you to notice why they work this way. But since you're multiplying by, like in the case of the first example, I started with $500,000, the principal, and I take that and I multiply by something. And notice in the simple interest formula, what I have here is it's 1 plus RT, which what that is saying is I'm going to take 1, which is like the mathematical equivalent to 100%, and I'm going to add the interest rate times time. So and again, the variables and what they stand for are all in the packet, but just since I haven't mentioned this yet in the videos, are in all of these videos is going to stand for the interest rate, or sometimes it's called the nominal interest rate, or the APR, which is just sort of like if you have an account there and you're told their interest rate, it's going to always be this nominal interest rate. But I'm being consistent in my use of R as being that nominal interest rate. And then T is going to be your time frame. And just something that is kind of important is that nominal interest rates are pretty much always given in the form of a yearly growth. So if you have an account and someone tells you it's 5% interest rate, that almost ubiquitously means that that's how much it's going to grow in a year. Um, but it can be contextual. Sometimes you might not be given, it might not be yearly, but in any question I'm going to give you in the homework or whatever, it's always going to be an annual rate. Or sometimes I'll just say this is the APR, which just stands for the annual percentage rate. Um, and as we talked about last week, what's important is if you have a 5% interest rate, when you're plugging that in for R into the formula, that has got to be plugged in as a decimal. And then the second factor in the equation is t, the time frame, which must be in years. So these are notes that I'll go ahead and fill in on the packet. Must be plugged in as a decimal number, and time must be in years. And really, the reason that that's so important is that if my interest percentage rate is based in years, so 5% per year, I want to multiply it by how many years I'm allowing it to grow. Not like, so say for example, we let this account sit for 3 months. That I would not want that to be my t, because that's not going to be a full year of growth. So if I plug that in for 3, that's always going to mean years in the context of the formula. And the last variable n is in the other formula. Well, I'll get to that later when we talk about compound interest. But basically, let's say we return to the previous situation. If I apply the formula instead of just doing what I did, what I would have is, well, the principal, $500,000 loan, multiplied by 1 plus RT. So basically, R was my interest rate 0.05, and T was how much time. So in the example that I posited, let's say we have $500,000 loan, don't pay it off for 1 year, and it's growing at 5%. This is what we get. But notice that what that's doing is it's going to take 1 plus 0.05 times 1, which all that amounts to is exactly what I did via the shortcut method we talked about, which is multiply by 1.05, which is $525,000. Or let's say I wanted to do it over 3 years. I could simply tweak the value of t in the formula, which would give me 3 years of that growth, which would just mean I like I said, it grew by $25,000. In simple interest, it's going to grow by the same amount every year. It's not going to, because we're not compounding. Our growth is always based on the principal. And most real accounts do not use simple interest because it doesn't really make sense on a financial side in most contexts to use simple interest, just due to the nature of how much you owe being not really, it doesn't really matter how much you started with, it matters more about what you currently owe, which is why compounding is typically a thing. But anyways, and actually one other thing I wanted to mention is a lot of times you may have seen like a simple interest formula before, and it might look a little different, but I just wanted to mention why it looks a little bit different than an alternative version. This is a version I've seen in a lot of textbooks in algebra classes, which is often called a simple interest formula, which is pretty easy to remember for PERT, as a mnemonic to help remember. I guess it's not really mnemonic, but whatever. But basically, interest is equal to principal times rate times time. And if you've seen this formula, this is the same formula, but what this formula does is it only calculates the interest that accrues in a simple interest situation. So if I was to apply that formula instead, what I would have is 500,000 times the rate times the time, and that would just simply give me how much interest generated. And notice that if I'm comparing these two formulas, the only difference is this one is, if I use the distributive property, is P times 1 is P plus PRT. So if I kind of am comparing these formulas, this would be the version that I have in the packet. But all this is saying is that I'm starting with the principal and adding the interest, which is given by PERT. So you can think of that as PERT plus, and that's like a lame hair cleaning shampoo product joke, I guess. But I've had a harder time making my lame jokes now that I've migrated to online. But anyways, it's the same formula as this one. And so I also, when it comes to you working on the homework or the final, I don't really care if you solve these things differently, or if you already know these concepts, you don't necessarily have to relearn it a new way. But my goal is to um, provide you with some different structure to help you get started. And I really think that, in each context, there's a formula for calculating the outcome. But understanding, the sense of it is important too. That's kind of what this video is focused. I'm trying to focus on is why do these make sense as well. And I'll try to wrap this up because it's getting quite long. But let's get into the compound interest formula, and then we'll try to wrap this up and look at some actual examples. I think it becomes a lot easier to understand what's going on when we look at some examples and throw some numbers into it, which is what I'm trying to do. But basically, the compound interest formula is a little bit different. It's meant to compensate for the repeated multiplication within a compound within such a situation. So if you kind of return to the math I was talking about when I was talking about when it would compound, basically what I did is I took, well, for the first year, it multiplied by 1.05. Then for the second year, it multiplied by 1.05. And the third year multiplied by 1.05. So if the interest is compounding, each year it's growing by 5% of the current value. And so it's going to form a stacking multiplication situation, which is just another word for compounding percentages. And basically what's going to happen is it's going to be an exponential growth function. Because another way that I could write that would be as an exponent, right? Because repeated multiplication, that's what an exponent means in math, and what one of the reasons why exponents became such a important and thing in algebra and financial mathematics in general. But basically, what I could see is when it's being compounded over 3 years, it's gonna give me a different answer than if it was behaving under simple interest over 3 years. So sorry, I was just trying to replicate those formulas and just do a little quick comparison. But because it's compounding, it's growing a little bit faster over time, and that's kind of what we see as described by this example graph, where it's showing the difference between an account which is growing under simple interest versus compound interest at 8% over a long period of time. And the difference, notice the difference, in the first 10 years is fairly negligible. They grow in a very similar rate, but as time progresses, as the balance grows, basically, it's going to grow by more and more and more, and that's where separation occurs over time. And this is why long-term loans, for example, like a home loan, a 30-year mortgage or whatever, can be quite the financial burden, is because as time progresses, the value of a compounded loan is, like, if you comparing the numbers here, is roughly triple the value if it was not being compounded. And so there's quite an extreme difference. And this is something that's important to be aware of, because a lot of people, as I said in the slide, struggle with paying interest their entire lives. And often it can be due to poor education or not really knowing what they're up against. When someone takes out a loan, it's just important to understand, what are the implications of accepting this loan at this interest rate, which is the importance of doing so. But what I wanted to get back to with the compound interest formula is, notice it's an exponential function, where the difference here is that t was being multiplied by r, because each year it grew by that percentage. And basically, if I wanted to grow by 5% over 3 years, I just multiply 5% times 3, which is 15%, and it gives me just a flat 15% growth. But with compound interest, if we use the same parameters, and n just stands for the number of times it's going to be compounded each year. In the example I posited, that was just 1. So for now, I'm going to leave n to be 1, but that would leave me with 500,000 times 1 plus r divided by n. And notice that in this formula, this is pretty much the same as the base of the simple interest formula. What I have is 1 plus 0.05, which basically is exactly what I did up here. It's going to grow by 5%. So that's 1.05. I can multiply by 1.5 to do that growth. And then in the exponent, it's going to be raised to the n times t power, where again, t is the number of years. So in the case of 3 years, what I wanted you to notice about how we could figure this out is this formula is going to do the same thing. It's going to take your interest rate basically, and it's going to multiply by the time frame. How many times am I applying this interest rate to it? And it's going to be exponential, which will have a graph that looks more like this as opposed to a linear function like in simple interest, which looks like this. So each of these just properly models the growth of the interest under those paradigms. And we're going to get that same answer that we got via just repeatedly multiplying by 1.05. So anyways, the formulas are designed to do exactly what we want in each context. And really what you need to know, what I recommend is, understand how to use the formulas, know what letters stand for what, and then just kind of understanding the context of when I'm supposed to use one or the other. Now the last formula we have here is what we refer to as a continuously compounded interest formula. And basically, this is a formula that describes what happens as we compound the account more frequently. And I'm going to go ahead and end this video because it's getting way too long, but we'll kind of look at this formula and look at what that means as we do a few examples. Because in order to really understand the compound interest formula, I think it's helpful to look at a few different situations so we can kind of tell what's happening and what changes about the math when we compound something more frequently.